Hello everyone. This lecture I'll be explaining for two subjects. They are both related to factorials somehow. So the first is what's called Wilson's theorem, and the other is an issue addressed in the concrete mathematics book. It was in one of the first few sections in chapter 4, probably 4.2, 4.3. So it's like find the powers of primes and factorials. So first I begin with Wilson's theorem. So this theorem basically states the following, that we have some p is a prime then we have p minus 1 factorial is congruent to -1 of p. So basically this is the theorem. So to prove this, we will have to prove that so to take the numbers here, so this p minus 1 is basically the numbers 1, 2, 3, and so on until p minus 1. So we have to show that this product is congruent to -1. So first we have to prove two things. So the first one, that there's no number that is congruent to, that is the inverse of itself, means that so there's no a, such that a inverse is congruent to a like p. This has very few exceptions, but we show them. So this we can basically prove by multiplying a in both sides. So we will get that a to the power of 2 is congruent to 1 mod p. And then so a squared minus 1 is congruent to 0 mod p. So a minus 1 times a plus 1 is congruent to 0 mod p. So basically it will happen only if a is congruent to 1 mod p. A is congruent to minus 1 mod p. Basically it will be if the number a is from these two. Otherwise, if we have we are using the a from these numbers, then this will never be true. So this is the first statement, and the second would be the inverse of a is actually it's a unique number, and this we already know from math complete theorem. So we can have so this is the inverse that we can calculate, and let's say like if we have two inverses. So the first inverse is, let's say, B1 and also B2. These are two different inverses. It means that B1 times A is equal congruent to 1 not P. Here also I'm assuming that the A is smaller than P. So it's still one of these numbers here. We also have like B2 is congruent to A. Sorry, B2 times A is congruent to 1 of P. So we have that B1 times A is congruent to B2 times A of P. And since like the A and P, so P is a prime number, so unless A is a multiple of P, then they are co-prime. And since the A is smaller than P, we have A smaller than P. So A is not a multiple of P. So basically we have the A co-prime of P. So here we can divide by this A and we can eliminate it without any harm. We have shown earlier. So basically we'll have this inverses has to be the same of P. So this proves that like any two distinct inverses cannot actually be distinct, so they have to be the same. So, for example, if we want the inverse of 2, there's exactly one number here that is the inverse of 2. And so the other, so as we know from the inverse, it goes both ways. So A inverse is equal to B, so B inverse will be equal to A. So from here we can make so this deduction. So all these numbers, 3 minus 2 minus 1. So here we assume that the P is a prime greater than so greater than 2, so it's an odd prime. So here we have these elements are P minus 2 plus 1. So they have this count, P minus 3. So these are the elements here. So basically each element here, we can make it in some unordered pair with its inverse. We have an inverse, and then some other A2 inverse, and so on. So the way like we can do this, because there's exactly one inverse, and the inverse goes both ways. So the inverse of this is this, and the inverse of this is this. So we cannot have a number that exists in more than one pair. And here the pairs also will have always like two distinct values because of this property that we proved here. And this. So there's no element that is then inverse of itself. So basically this will, these sets will, or this unordered pairs will contain all the elements from here. And each of these pairs, when we multiply it, the numbers in, we get a result of 1, here a result of 1, and so on. This all, of course, is taken modulo p. So we end up, when we multiply all of these numbers, we get a result of 1 mod p. And this also, when we multiply by the 1, it remains 1 mod p, and then we end up having p minus 1. So basically p minus 1 factorial. This is p minus 1 times p minus 2. And p minus 2 factorial, as we've shown here, is the product of all of these numbers, which is congruent to 1. So, and this is also congruent to negative 1, not 2. So basically this proves the theorem, the Wilson's theorem. So this was it for the Wilson's theorem. Now we move to the second point, which is the factorial factorization. So we begin by having, let's say we have n factorial, and we want to factorize this number. So it's basically, it will be f2 to the power f2, 3 to the power of 3, 5 to the power of 5, and so on. And if we can just multiply all indices, full PR or alpha. And this, so all the primes here has to be all the primes before n, before equal to n. So any prime occurring from 1 to n has to appear somewhere here. So basically we'd like to know what are these alpha weights. So the way to know this would be that here. So we have, like, let's say in the, if we have some number n, we'd like to count how many numbers are so divisible by 2. This will be n over 2. So each of these number will add 1 to this value alpha 1. And then those are the numbers from that are divisible by 4. Each of these will add 2 to the value here. Sorry, to the alpha. And this n over 8. So all the multiples of 8 will add the value 3, and so on. So I will add so the way we can visualize this, we can have an example. So if we have n is equal to 20, I will list here. So I'll not list the odd numbers because they won't add any power of 2. So if we put the even numbers, then So here we have the power of 2 in the 20 factorial. So the 2's will come only when we multiply these elements together. So this has a power of 2 is equal to 1, here is equal to 2, here's 1, 3, 1, 2, 1, 4, 1, and 2. So because this number is divisible by 4, which is 2 to the power of 2, and the 16 is divisible by 2 to the power of 4, and that's why we have the 4 here, and so on. So basically the contribution of the multiplying 2 is adding 1 to the alpha. And multiply 4, it's adding 2 to the alpha, and so on. Basically here, when we make like n over 2, we basically go through all these numbers and we subtract like this one. So basically when we add n over 2, we basically add 1 for each of these numbers. And then when we go for like n to the 4, so the multiples of 4, which are these numbers. So these we will also add 1 for each of them. So we can get 1, and for the multiples of 8, or here and here, so we'll add also so 1 to each of them. And basically here, so n to the power 16, which is 5, here we'll add another value. So basically this will count like the powers, as you can see. So here, so because this will make a contribution of only 1 to the exponent, means it's only a multiple of 2 and not a multiple of 4. So it will only be counted here. And for example, let's take the 8. So the 8 will add the value 3 to the exponent of 2. So this we will count it by counting. So it means that the number is divisible by 8, but not divisible by 16. And it's also divisible by 4 and 2. We'll count it once here, and once here, but we will not count it in the next. So this is how we get the 3. So basically it keeps going on. So using this formula, we can basically count what is the power of like 2 in the input here. And we can repeat the same process for all the primes, so in order to know all the outputs. So basically it would go something like that. And P. So this is like the alpha of the prime P in the factorization of n factorial. So here we factorize n factorial. We'll have P to the power alpha P, and it will be the same for all of them. So the formula that we have found here for this f is basically goes to count the number of powers of P for all the possible powers. basically do it like that. And say up to, so the limit would be log n, basically. Maybe can even throw this in the cooler. Basically, this formula we can use to find the power of some prime p in when we factorize n factorial. So this formula will calculate it properly. So that's it. I hope you enjoyed it, and thanks for listening.